You begin in darkness, not an empty darkness, but a deep and patient one. It is the kind of darkness that holds stories. Around you, scattered like seeds across an endless field, drift countless stones. They turn slowly. They do not hurry. They do not speak. And yet they have been here longer than mountains, longer than oceans, longer even than life itself. These are asteroids, the quiet rocks between the planets. If you imagine the solar system as a house still under construction, these are the leftover bricks. They formed more than 4.5 billion years ago, when a vast cloud of gas and dust collapsed under its own gravity. At the center, the sun ignited. Around it, grains of matter clung together, gently at first, then more firmly, building pebbles into boulders, boulders into worlds. But not everything became a planet. Between Mars and Jupiter lies a wide region called the asteroid belt. There, gravity never allowed a single large world to fully form. Jupiter, immense and commanding, stirred the material with its pull, preventing it from settling into one body. So what remains are fragments, thousands upon thousands of rocky relics, each one a survivor of the solar system's childhood. You drift among them now in your imagination. Some are small as houses. Others stretch hundreds of kilometers across. A few are nearly spherical, shaped by their own gravity into quiet, rounded forms. Most are irregular, like broken shards of pottery. Their surfaces are scarred by collisions, the slow, steady tapping of time. They are not all the same. Some asteroids are made mostly of rock, silicate minerals similar to those beneath your feet on Earth. These are called stony asteroids. Others are darker, rich in carbon compounds, carrying complex organic molecules that once drifted in the early solar nebula. And then there are the metallic ones, heavy with iron and nickel, gleaming faintly beneath a coat of dust. You imagine touching one. It feels cold, far colder than any winter night. In space, without air to hold warmth, temperature swings wildly. In sunlight, an asteroid's surface may heat to over 100 degrees Celsius. In shadow, it can plunge below -100. There is no atmosphere to soften these extremes. No wind. No sound. Just stillness. And yet, inside some of these rocks, there is water. Not liquid water flowing freely, but water locked within minerals, or frozen as ice beneath dusty layers. In the early solar system, icy bodies formed farther from the sun, where temperatures were lower. Some of them drifted inward. Some collided. Some broke apart. And pieces of them remain here still. Water, the same molecule that fills your cells, hiding quietly inside stone. You begin to sense why these rocks matter. They are time capsules. When scientists study meteorites, fragments of asteroids that fall to Earth, they find tiny grains older than our planet. They measure isotopes, the subtle variations in atomic weight, and reconstruct ancient histories. From these samples, you learn how the elements were distributed, how planets differentiated into cores and crusts, how even the ingredients for life may have been delivered by impacts long ago. Asteroids are not debris. They are memory. Some carry platinum group metals more concentrated than in most places on Earth. Platinum, iridium, rhodium elements used in electronics, catalysts, clean energy technologies. On Earth, these metals are rare because they sank into the molten core during planetary formation. But smaller asteroids never melted fully. Their metals remain accessible, closer to the surface. In a metallic asteroid, you might find iron and nickel in abundance, the very materials used to build bridges, skyscrapers, spacecraft. You float gently beside one such object now. It rotates slowly, once every few hours. Its gravity is faint, almost a suggestion rather than a force. If you stood upon it and jumped, you might drift away into space. And still, it continues its orbit around the Sun, patient and predictable. There are near-Earth asteroids, two bodies whose paths bring them close to our planet. They cross Earth's orbit, sometimes coming nearer than the Moon. Astronomers track them carefully, mapping their trajectories, calculating probabilities decades into the future. Most pose no danger. They simply pass by, cosmic neighbors moving along their routes. But their closeness changes something. Distance, in space, is everything. To reach the surface of the Moon requires immense energy. To land on Mars, even more. Yet some near-Earth asteroids require less energy to reach than the Moon itself. They are small targets, yes, but in terms of fuel and engineering, they may be more accessible than you expect. You begin to see them differently. Not as threats. Not as random rubble. But as stepping stones. Imagine harvesting water from one, splitting it into hydrogen and oxygen rocket fuel. Imagine extracting metals without digging deep into Earth's crust. Imagine building structures in orbit from materials already in space, instead of launching every kilogram from the ground against gravity's pull. Each kilogram launched from Earth costs enormous energy. Rockets burn thousands of tons of propellant to lift a relatively small payload. Gravity is a powerful gatekeeper. But in the low gravity of an asteroid, lifting material into space requires almost nothing by comparison. The rocks you drift beside are quiet, but they are not empty of possibility. You notice how slowly everything moves here. There is no rush. Orbital periods span years. Collisions are rare but transformative. Time feels stretched, like a long exhale. In this calm, you understand something subtle. The solar system did not discard these stones. It preserved them. They are the leftovers, yes, but leftovers often contain the recipe. Inside them is information about how planets form. Inside them is material that could support journeys beyond Earth. Inside them is water, metal, carbon, the building blocks of habitats, fuel depots, laboratories. They are small worlds waiting to be understood. And yet, for billions of years, they have simply circled the Sun, unnoticed by anything but distant stars. No machines have touched them. No tools have struck their surfaces. They remain as they were when Earth was molten. You feel both humbled and curious. Because to reach them, to truly use what they hold, requires more than rockets. It requires intention. It requires engineering. It requires a reason strong enough to leave the cradle of Earth and work in the silence of vacuum. For now, they drift. But humanity, too, drifts in thought. You begin to sense that our own planet, vibrant and generous, may not always provide everything we need. The metals in your devices, the energy in your cities, the materials in your buildings, all drawn from a finite sphere. And as you float among these ancient rocks, you feel the faint stirring of a new question forming, gentle as starlight. If Earth is abundant yet limited, could these quiet stones become the next frontier where need and curiosity meet? You return now to Earth. After drifting among ancient stones, you feel the familiar pull of gravity again, steady, comforting, constant. Beneath your feet is soil. Beneath that, layers of rock folded over billions of years. Beneath that, deeper still, a molten heart of iron turning slowly in darkness. Earth feels vast. Oceans stretch beyond sight. Mountains rise into cloud. Forests breathe quietly in green rhythms. It is easy to believe there is always more. But when you look gently, closely, you begin to see the arithmetic beneath the beauty. Every object around you, your phone, your computer, the wiring in your walls, the battery in an electric car, begins somewhere underground. Copper veins running through stone. Lithium salts dissolved in desert brines. Rare earth elements scattered thinly through ancient crust. Rare earth elements are not truly rare in presence. They are rare in concentration. They hide dispersed, like sugar dissolved in a vast sea of rock. To gather them, you must move mountains. You must crush, separate, refine. It takes energy. It takes water. It leaves scars. You imagine standing at the edge of an open-pit mine. The earth is carved into terraces like a giant amphitheater. Trucks crawl along spiral roads, carrying loads of ore. Dust rises. Machines hum. It is not evil. It is not cruel. It is simply the cost of extraction. And demand keeps rising. As populations grow and technology deepens its roots into daily life, the need for metals increases. Renewable energy systems, solar panels, wind turbines, electric grids require copper, neodymium, silver, cobalt. The shift toward cleaner energy is real and necessary, yet it, too, depends on materials drawn from the ground. You notice the paradox. To protect the planet, you must use it. Lithium-ion batteries power the transition away from fossil fuels. But lithium must be mined or evaporated from brines. Cobalt strengthens battery stability, yet much of it comes from regions where mining conditions are harsh and human labor is strained. Even aluminum, light and abundant, requires vast electricity to refine from bauxite ore. You begin to see Earth not as infinite, but as finite and precious. The crust of the planet is thinner than you might imagine. Compared to the Earth's total radius, the layer where all mining occurs is like the skin of an apple. Within that thin layer lie the resources that power civilization. And once high-grade deposits are depleted, extraction becomes more difficult. More rock must be processed to obtain the same amount of material. This is called declining or grade. It means that over time, the richest, easiest deposits are used first. What remains is leaner, harder to reach, more energy-intensive to refine. Energy itself is another quiet limit. For centuries, fossil fuels, coal, oil, natural gas have powered industry. They are ancient sunlight, stored in chemical bonds. But burning them releases carbon dioxide, altering the delicate balance of Earth's atmosphere. You have seen the evidence in warming temperatures, shifting weather patterns, melting ice. The atmosphere is thin too. A fragile envelope, only about 100 kilometers thick before space begins in earnest. All of human history unfolds beneath this narrow sky. You feel gratitude for it. And yet, the more you think, the more you sense tension. Billions of people seeking better lives. Infrastructure expanding. Technology multiplying. Each improvement draws on Earth's material bank. You are not separate from this. The device playing this narration contains gold in its connectors, silicon in its chips, indium in its touchscreen. The electricity flowing into it may come from coal, wind, sunlight, or uranium. Every convenience rests upon extraction somewhere. It is not a story of blame. It is a story of scale. Earth can provide. But Earth is one planet supporting billions of humans and countless other species. Forests cannot regrow instantly. Mineral deposits do not replenish on human timescales. Oil takes millions of years to form. Metals forged in ancient supernovae cannot be recreated easily. You begin to ask a gentle question: what if some of the pressure could be eased? Not by abandoning Earth, not by exploiting without thought, but by expanding the source of materials beyond this single sphere. You remember the asteroids, metal-rich, water-bearing, largely untouched. In space, there is no atmosphere to pollute, no ecosystems to disturb, no rivers to contaminate. Mining in space would not be simple or impact-free, but its environmental footprint would differ profoundly from terrestrial extraction. Launching material from Earth requires enormous energy because of gravity. But retrieving certain materials from near-Earth asteroids may, in theory, require less energy overall than lifting the same mass from deep within Earth's gravity well. The concept feels radical at first. Mines in space. Factories in orbit. Water harvested from rock drifting between planets. And yet, humans have always expanded resource frontiers. Once, coal replaced wood as forests thinned. Later, oil replaced coal in many uses. Solar and wind now supplement fossil fuels. Each shift required new tools, new imagination. Perhaps the next frontier is not deeper underground, but upward. You breathe slowly. Scarcity, you realize, is not panic. It is information. It tells you that choices matter. It invites innovation. It asks you to think longer than the next decade. Earth remains abundant in sunlight, wind, geothermal heat. It remains the only known world with oceans and forests and life. The goal is not to strip it bare. The goal is to protect it, to allow ecosystems to heal, to reduce destructive extraction, to balance growth with stewardship. Space resources could become part of that balance. If metals for satellites, space stations, and solar arrays were sourced from asteroids, fewer launches from Earth would be needed. If water for deep space missions were mined in orbit, rockets would not need to carry every drop from the surface. The pressure would not vanish. But it might shift. You imagine a future where heavy industry for space infrastructure happens beyond Earth's biosphere, leaving this planet primarily for life, culture, and care. It is a gentle vision. Not an escape. Not abandonment. But redistribution. Yet even as the idea settles, you sense another layer of complexity. Reaching asteroids is not trivial. Mining them is not simple. The environment of space is harsh vacuum, radiation, extreme temperature swings. Human workers cannot stand easily on their surfaces. If resources are to be gathered there, something else must do the work. Machines. Machines that do not breathe. Machines that can endure cold and heat. Machines guided by intelligence, perhaps even learning. As your thoughts slow, you feel the next chapter approaching like a quiet sunrise. If Earth is not enough, if the quiet rocks between planets hold promise, then who, or what, will touch them first? In the silence between heartbeats, you begin to imagine the machines that work without air. You begin with a simple image. A machine, alone in silence. No air surrounds it. No wind brushes its surface. No sound carries from its movements, because sound itself requires air, and here there is none. It operates in vacuum, a place so empty that even breathing is impossible. And yet, it works. On Earth, machines are built for a world of atmosphere and gravity. They rely on air for cooling. They depend on weight for traction. Hydraulic systems push against resistance. Engineers design them knowing that if something overheats, air will carry the warmth away. But in space, there is no such comfort. Heat does not drift gently off a surface. It must radiate away slowly as infrared light. If a motor warms too much, it cannot rely on breeze or convection. Engineers must design radiators, flat panels that glow faintly with waste heat, releasing energy into the dark. You picture a robotic miner landing softly on an asteroid. Its descent is careful, almost delicate. The asteroid's gravity is so weak that even a gentle push could send it drifting away. So the machine anchors itself. Harpoons, drills, gripping claws, tools designed not to stand upon a surface, but to hold onto it. Because in microgravity, there is no firm footing. If you swing a hammer on Earth, your weight keeps you grounded. On an asteroid, striking the surface might push you backward instead. So robots must brace themselves. Some designs include counter-rotating arms to cancel momentum. Others drill slowly, pressing inward with steady force, careful not to rebound. The physics is different. The choreography must change. Radiation is another quiet challenge. Beyond Earth's magnetic field, high-energy particles stream from the Sun and from distant cosmic events. These particles can damage electronics, flipping bits in memory, degrading circuits over time. So space robots were shielding layers of aluminum, specialized materials, redundancy in critical systems. Redundancy is a gentle word for backup. Where humans can adapt instinctively, machines must anticipate failure in advance. Important components are duplicated. Systems monitor one another. If one pathway fails, another takes over. On Earth, a broken machine can be repaired by a technician with tools in hand. On an asteroid millions of kilometers away, repair may not be immediate. Communication signals travel at the speed of light, but even light takes time. Depending on distance, commands from Earth may arrive minutes later. You send a signal. You wait. The robot responds. This delay means the machine cannot depend entirely on human control. It must think, at least in limited ways, for itself. Autonomy becomes essential. You might imagine autonomy as a spark of awareness, but in engineering it is more practical. Sensors gather data: cameras, LiDAR, spectrometers, force detectors. Software interprets patterns. If the drill encounters harder material, it adjusts torque. If a wheel loses traction, it changes angle. If sunlight fades, it conserves energy. Artificial intelligence, in this context, is less about consciousness and more about decision-making under uncertainty. The robot must recognize terrain. It must distinguish shadow from rock, dust from solid surface. It may map its environment in 3 dimensions, building a digital memory of its surroundings. You think of it as a quiet mind, built of silicon and code. Power is another question. Far from Earth, solar panels become lifelines. Wide, flat wings unfold to catch sunlight. On some missions, nuclear power sources provide steady energy, unaffected by shadow. But on an asteroid, where rotation may bring hours of darkness, energy storage matters. Batteries must endure extreme temperatures. Systems must sleep and wake in rhythm with sunlight. Even movement requires rethinking. Wheels, useful on Earth, may not function well in loose regolith, the dusty, fragmented surface material covering many asteroids. Some robots hop gently from place to place, using small bursts of gas. Others crawl slowly, anchoring before each motion. Some concepts involve tethered systems, where one module grips while another advances. There is creativity in this engineering. You begin to see these machines not as cold devices, but as explorers in their own right. They extend human reach. They carry instruments into places no astronaut could easily stand. They do not need air. They do not need warmth. They do not fear isolation. Yet they remain connected to you. But true experience only comes in space itself. You feel the magnitude of the challenge. And yet, humanity has already sent robotic explorers to Mars, to comets, to the outer planets. Rovers traverse Martian soil. Probes have landed on cometary nuclei. Each mission refines knowledge. Each success builds confidence. Asteroid mining robots are not a sudden leap. They are the next step in a long progression. Still, something deeper stirs in your thoughts. For a robot to work effectively on an asteroid, it must adapt. Surfaces vary. Composition differs. Unexpected obstacles arise. The more distant the mission, the less feasible constant human oversight becomes. So autonomy must deepen. Machine learning algorithms may allow robots to improve performance over time. They may analyze drilling efficiency, adjust parameters, optimize energy usage. They may share data with other machines, forming a network of experience. In this way, robots begin to build upon one another's knowledge. You pause with this idea. Machines building experience. Machines refining technique. Machines working in silence, sustained by sunlight and code. It feels both extraordinary and inevitable. And yet, there remains a fundamental problem. Even the most capable robot must first reach the asteroid. It must land without drifting away. It must attach securely to a body whose gravity barely whispers. How do you hold onto a moving mountain that does not wish to hold you back? As you drift toward rest, the question lingers softly, leading you into the delicate dance of catching something that barely feels your touch at all. Oh, you approach the asteroid slowly. There is no roaring engine, no dramatic descent through atmosphere. There is only careful adjustment, small bursts of thrusters, gentle corrections in velocity. In space, speed is relative. If you match the asteroid's orbit around the Sun, if you match its own subtle motion, you are no longer chasing it. You are drifting with it. It looks solid, ancient, immovable. But it is not still. Most asteroids rotate. Some spin once every few hours. Others tumble unpredictably, like loose stones tossed in slow motion. From a distance, they seem calm. Up close, you see the rotation, a slow turning against the starfield. You must respect this motion. On Earth, you land on a surface that is not only massive but anchored by gravity. The planet's weight holds you close. Even the Moon, with only 1/6 of Earth's gravity, still offers firm footing. But an asteroid may have gravity so weak that a human could leap into orbit with a single strong jump. Gravity here is not a firm handshake. It is a suggestion. If you try to land too quickly, you bounce. If you fire thrusters too hard, you drift away. The escape velocity, the speed needed to leave the asteroid entirely, may be only a few centimeters per second. Slower than a casual walk. So you approach with patience. Engineers call this rendezvous in docking. It is a dance of velocities. You calculate the asteroid's orbit around the Sun. You measure its rotation rate. You align your spacecraft so that when you descend, you are not fighting its spin but matching it. Imagine stepping onto a slowly turning carousel. If you time it well, you move with it. If you mistime it, you stumble. Asteroids do not provide rails or smooth platforms. Their surfaces are irregular ridges, craters, loose gravel called regolith. Some are rubble piles, collections of fragments loosely bound by gravity. They are not single solid rocks but aggregates, held together gently. Touching such a body must be done with care. You picture a robotic lander extending its legs. At the moment of contact, it does not simply rest. It fires small anchoring devices, harpoons or screws, to secure itself. Without anchoring, even the act of drilling could push it backward into space. Newton's third law whispers here, for every action, an equal and opposite reaction. If the robot pushes downward with force, the asteroid pushes upward with equal force. But because the asteroid's gravity is weak, the robot cannot rely on weight to keep it pressed to the surface. It must create its own grip. Some mission concepts involve nets, wrapping gently around smaller asteroids. Others envision robotic arms that clasp boulders like careful hands. There are proposals to enclose an asteroid inside a bag-like structure, stabilizing it for processing. It feels almost tender, this need to hold gently but firmly. Rotation adds another layer of complexity. If an asteroid spins, different parts of its surface move at different velocities. Near the equator of a fast-spinning asteroid, centrifugal force may counteract gravity. Loose material can migrate toward the equator, forming ridges. In extreme cases, small fragments may escape entirely. So before landing, you study the spin. You map it from afar. You watch how sunlight glints across its surface, tracking rotation. You send probes to orbit, measuring its gravitational field. Every data point refines your understanding. Inertia becomes a quiet companion in your thoughts. In space, objects continue moving unless acted upon by force. There is no atmospheric drag to slow them. Once you are traveling alongside an asteroid, you share its motion around the sun tens of kilometers per second, yet relative to each other, you feel nearly still. This is the strange beauty of orbital mechanics. Enormous speeds coexist with gentle encounters. You realize that catching an asteroid does not mean grabbing it out of space like a thrown ball. It means synchronizing with it. Matching its path so precisely that, from your perspective, it floats calmly beside you. In some visions of the future, engineers may alter an asteroid's orbit slightly, nudging it into a more convenient path. Small, continuous thrust over months could shift its trajectory. Gravity tractors, spacecraft hovering nearby, could use their own mass to exert tiny gravitational pulls over time. The adjustments are subtle. Space rewards patience. There are risks, of course. A miscalculation in velocity could send a spacecraft drifting off course. A poorly anchored drill could destabilize a rubble pile. Extracting material might alter the asteroid's rotation if not managed carefully. So you design systems that monitor constantly. Gyroscopes measure spin changes. Thrusters compensate gently. Anchors adjust tension. Everything is feedback and balance. You begin to appreciate how different this environment is from Earth. On Earth, friction is abundant. Air slows motion. Gravity presses you down. In space, motion persists. Forces must be applied deliberately and precisely. It is less like construction on solid ground and more like choreography in slow motion. You imagine standing, or rather floating, beside a rotating boulder larger than a city block. Above you, stars do not twinkle, there is no atmosphere to distort their light. The sun casts sharp shadows. Dust drifts lazily when disturbed, falling back slowly in graceful arcs. In this place, every push matters. And yet, once secured, the asteroid becomes less a drifting mountain and more a quiet partner. Anchored machines can begin their work. Drills can penetrate. Heaters can warm icy veins. Conveyors can guide fragments into processing units. The first challenge is not extraction. It is connection. To hold onto something that barely holds onto itself requires understanding of physics, of material strength, of motion. It requires humility before forces that operate silently and persistently. You feel that humility now. Because the asteroid is not resisting you. It is simply obeying the laws of nature. Gravity, momentum, rotation, these are not obstacles. They are conditions. And when you align with them, when you move in harmony with their rules, the impossible becomes manageable. The moving mountain becomes approachable. Still, anchoring is only the beginning. Once attached, once stable, another question arises softly in your mind. What lies inside these stones that makes the effort worthwhile? What hidden reservoirs could transform distant rock into something as vital as breath? As the asteroid turns beneath imagined starlight, you begin to sense the quiet presence of something essential, something frozen, waiting, and surprisingly familiar. Water in the sky. You begin with a simple truth. Your body is mostly water. Every breath you take depends on it. Every thought you think is carried through cells cushioned in it. On Earth, water feels ordinary. It falls from the sky. It flows through rivers. It fills oceans so vast they reshape continents. But in space, water is not ordinary. It is treasure. As you drift again beside the anchored asteroid, you imagine looking not only at its surface but inside it. Many asteroids, especially the darker, carbon-rich ones, contain water bound within their minerals. Some formed far from the sun, where ice could survive. Others absorbed water chemically, locking it into crystal structures billions of years ago. The water is not flowing. It is not liquid in streams. It is frozen, or trapped inside rock like memory held in stone. And yet, it is there. Scientists detect this hidden water by studying reflected sunlight. Certain wavelengths are absorbed by hydroxyl groups, combinations of hydrogen and oxygen bonded within minerals. Spacecraft instruments measure these subtle fingerprints, revealing hydration where the eye sees only gray dust. You imagine heating a sample of that dust. As temperature rises, water molecules begin to escape. They turn to vapor, drifting gently away. Capture that vapor in a sealed chamber. Cool it. Condense it. Now you have liquid water. This process may sound simple, but in space it transforms possibility. Because water is not only for drinking. Water is hydrogen and oxygen. If you pass an electric current through water, a process called electrolysis, you separate it into its two components. Hydrogen bubbles at one electrode. Oxygen at the other. Two invisible gases, each with power. Hydrogen is light and energetic. Oxygen supports combustion and breathing. Together, when recombined, they release enormous energy. Liquid hydrogen and liquid oxygen have powered some of the most powerful rockets ever built. So water becomes fuel. You begin to see the chain of meaning. If you can mine water from an asteroid, you can produce rocket propellant in space. Spacecraft traveling deeper into the solar system would no longer need to carry every drop of fuel from Earth's surface. They could refuel in orbit, like ships stopping at a harbor. Imagine a network of depots, small stations near asteroids or in stable orbits, storing tanks of hydrogen and oxygen. A spacecraft bound for Mars stops, refuels, and continues. The amount of mass launched from Earth decreases. The cost shifts. The architecture of exploration changes. Water also becomes air. Oxygen released from electrolysis can support astronauts. Hydrogen, combined with carbon dioxide exhaled by humans, can be used in chemical processes to regenerate water. closed-loop life support systems begin to form, reducing dependence on constant resupply. Water shields, too. Radiation in space is persistent. High-energy particles pass through metal walls. But water, rich in hydrogen atoms, is an effective radiation shield. Surrounding living quarters with water tanks can reduce exposure. In this way, the same substance that fills your cells becomes armor against cosmic rays. You begin to feel how central water is. On Earth, it is abundant enough to seem mundane. In space, it is structure, fuel, breath, protection. Some asteroids may contain significant quantities of ice beneath their surfaces, especially those originating from the outer solar system. Others may hold smaller amounts, but even a few percent by mass can represent thousands of tons in a sufficiently large body. And in microgravity, lifting that water into storage tanks requires little energy compared to launching it from Earth. You imagine the first robotic system dedicated entirely to harvesting water. It anchors gently, drills shallow boreholes, inserts heaters. As the ice sublimates, turning directly from solid to vapor and vacuum, the vapor is guided into containment systems. Filters remove dust. Condensers cool the vapor back into liquid. Solar panels gleam nearby, providing power for heating and electrolysis. The process is slow, careful, rhythmic. Water collected over weeks becomes propellant for future missions. It becomes life support for distant crews. It becomes a resource that reduces the gravitational burden of Earth. You feel something shift inside your imagination. Distance shrinks. The solar system, once vast and unreachable, begins to feel networked. Instead of isolated missions carrying everything from home, you envision a web of resource nodes, asteroids providing water, perhaps the Moon offering additional reserves, Mars with its own frozen deposits. Exploration becomes less like a sprint and more like settlement. And there is another layer. Many scientists believe that water on Earth may have been delivered, at least in part, by asteroid impacts billions of years ago. In that ancient era, icy bodies collided with the young planet, contributing to the formation of oceans. If so, then mining water from asteroids is not stealing from elsewhere. It is reconnecting with the original cycle. The water in your body may once have drifted through space. That thought settles softly. Still, harvesting water is not without challenge. Dust can clog mechanisms. Temperature extremes complicate storage. Liquid hydrogen must be kept at extremely low temperatures to remain stable. Systems must prevent leaks in vacuum. Every kilogram of equipment must function reliably without constant human maintenance. But none of these obstacles are impossible. They are engineering problems, intricate, demanding, but solvable with patience. You sense how foundational this step is. Before metals, before vast structures, water may be the first true resource harvested in space. It is versatile, essential, transformative. As tanks fill slowly in your imagined station, you picture a spacecraft arriving. It docks quietly. Hoses connect. Cryogenic fuel flows. The craft, once heavy with the burden of Earth's gravity, now receives what it needs from the quiet rock nearby. A new rhythm of travel begins. And as this rhythm settles in your thoughts, another realization rises gently. If water can be extracted and turned into fuel and air, what of the metals embedded in these asteroids? Iron older than continents. Nickel forged in ancient stars. Materials not for burning, but for building. Water may open the door, but metal may shape what stands beyond it. As the imagined depot glows faintly in sunlight, You feel your mind turning toward the solid heart of these cosmic stones, toward the idea of forging structures not on Earth, but in the open silence of space itself. You begin with weight. Not the weight you feel in your body, pressed gently toward Earth's center, but the idea of weight, of substance, of density. Metal carries that feeling. Iron in a bridge. Steel in a skyscraper. The quiet strength hidden inside machines. Now imagine iron that has never rested beneath a sky. Some asteroids, especially those called M-type, are rich in metal. They may be fragments of ancient protoplanets, bodies that once grew large enough to begin separating into core and crust. In those early days of the solar system, heat from radioactive decay and collisions melted interiors. Heavy elements like iron and nickel sank inward, forming metallic cores. Then came disruption. Violent impacts shattered some of these young worlds. Their rocky mantles were stripped away, leaving exposed cores drifting through space. What remains today are metallic asteroids, relics of planetary hearts, wandering in silence for billions of years. You drift toward one now in your thoughts. Its surface gleams faintly where dust has been disturbed. Beneath that thin coating lies iron-nickel alloy, similar to the material that composes Earth's own core. This metal was forged in ancient stars, in supernovae that exploded long before the sun was born. When you touch it in imagination, you are touching starlight made solid. On Earth, extracting metal requires immense effort. Ore is mined, crushed, transported to smelters. There, furnaces roar. Coal or natural gas burns, raising temperatures high enough to separate metal from rock. Impurities are removed. Slag is discarded. Smoke rises into atmosphere. But in space, the process changes. There is no air to carry smoke. No oxygen to support combustion. Traditional smelting, dependent on chemical reactions with carbon, must be reimagined. Yet space offers its own furnace. Sunlight. At Earth's distance from the Sun, each square meter in direct sunlight receives about 1,360 watts of energy. In vacuum, with no atmosphere to scatter light, that energy arrives undiminished. Using mirrors or lenses, engineers can concentrate sunlight into a small area, raising temperatures dramatically high enough to melt many metals. You picture a large reflective dish unfolding beside the asteroid, like a silver flower. It focuses sunlight onto a crucible filled with metallic grains. Slowly, the grains soften, then liquefy, forming a shimmering pool. In microgravity, molten metal behaves differently. On Earth, gravity pulls liquid downward, shaping it into puddles. In space, surface tension dominates. Liquid forms spheres, trembling gently. Containment systems must guide and hold the molten material. Magnetic fields may help shape and stabilize it, especially for iron-rich alloys. There is elegance in this. No roaring blast furnace. No smoke stacks. Just concentrated sunlight and careful control. Refining metal in space could involve separating impurities through controlled heating, allowing lighter elements to vaporize and be captured elsewhere. It might involve additive manufacturing, 3D printing, where layers of metal are deposited precisely, forming beams, panels, or structural components directly from raw material. Additive manufacturing changes the philosophy of construction. Instead of carving shapes from large blocks, you build structure layer by layer, like weaving solid matter. In microgravity, without the need to support weight during fabrication, designs can be lighter, more intricate. Long trusses for solar arrays. Large antenna reflectors. Frameworks for habitats. You begin to see factories forming in orbit, not enclosed buildings, but distributed systems. One module mines and processes metal. Another shapes it. Robotic arms assemble finished parts into larger structures. Because launching metal from Earth is expensive, every kilogram lifted from Earth must fight gravity. Rockets burn vast quantities of propellant just to escape the atmosphere. If raw material for space infrastructure can be sourced in space, the economics shift. Massive structures, kilometers long, perhaps become more feasible. You imagine building a spacecraft in orbit using metal mined from an asteroid. But challenges remain. Mining metallic asteroids requires cutting, drilling, fragmenting dense material. Tools must withstand wear. Dust and fragments must be managed carefully in microgravity to prevent uncontrolled debris. Processing systems must operate reliably over long durations. Energy supply must be steady. Concentrated sunlight works well closer to the sun, but farther out, intensity decreases. Nuclear reactors may supplement solar arrays for distant operations. You recognize that none of this is simple. Yet neither is it fantasy. On Earth, industries evolved over centuries, from primitive furnaces to modern steel plants. In space, development may begin small. Experimental processing units. Limited-scale production. Gradual expansion as confidence grows. The first metal printed in space from asteroid material might be modest, a bracket, a beam, a connector. But that small piece represents a profound shift. It means material is no longer entirely earthbound. You reflect on the continuity of elements. Iron in your blood carries oxygen through your body. Iron in asteroids formed in stellar explosions. The same element links biology and cosmology. If you build spacecraft from asteroid iron, you are shaping star remnants into vessels of exploration. The boundary between natural and constructed begins to blur. Factories without smokestacks. Production lines lit by sunlight instead of fire. Robots guiding molten metal in silence. Structures growing slowly against the backdrop of stars. You feel the scale expanding. Water provided fuel and breath. Metal provides skeleton and skin. Together, they form the foundation of infrastructure beyond Earth. And with infrastructure comes permanence. A refueling station is temporary until it is resupplied. A metal framework, once built, endures. A factory in orbit suggests continuity and ongoing presence rather than a fleeting mission. As your thoughts settle, you begin to envision these first true space factories, places where raw asteroid material is transformed into components, where machines assemble new machines, where construction happens far from Earth's gravity. Who'll design them? Who'll fund them? Who'll oversee their careful growth? The metal cools in your imagined crucible, solidifying into form. And in its quiet strength, you sense the outline of something larger taking shape, the first workshops beyond the sky. You begin with a vision. A factory not grounded, but drifting gently in orbit. It has no roof. No walls in the traditional sense, the sky itself is its ceiling. Beams of sunlight shine on polished metal surfaces. Robotic arms move slowly, deliberately, orchestrating a quiet construction ballet. Everything hums softly in microgravity, a rhythm of machinery and patience. This is the first space factory. You imagine its core, a module dedicated to raw material intake. Here, metal and water harvested from asteroids arrive, carefully stored and prepared for processing. Sheets of asteroid iron, dusted with regolith, wait to be melted or sintered. Water arrives as ice or vapor, ready for electrolysis. Every resource has purpose. Nothing is wasted. Adjacent to this intake module, additive manufacturing units lie in patient readiness. Long trusses, panels, habitat segments emerge layer by layer. The printers do not roar like terrestrial machines. There is no clanging, no smoke. The process is quiet, almost meditative. In microgravity, the metal holds its shape naturally, surface tension guiding molten droplets. Each printed layer bonds seamlessly, forming structures that will support weight, resist radiation, and endure the silence of space. Robotic arms extend gracefully, assembling components. Mirrors for solar concentrators unfold like delicate petals, panels snap into place with precise, deliberate motion. Cameras observe every movement, sensors feed data into software systems, and tiny corrections are applied in real time. Machines build other machines. Efficiency emerges organically. You notice the subtle choreography. A robotic manipulator reaches for a component, another guides it into alignment. Magnets, clamps, and soft gripping surfaces hold parts gently. Momentum must be managed carefully. Even the smallest push in microgravity can send a half-assembled segment spinning. Every motion is a conversation with physics. In this quiet ballet, humans are present too, but their role has shifted. They do not wield hammers or climb scaffolding. They design, program, and oversee. They plan sequences, monitor systems, and intervene remotely when necessary. The factory operates continuously, following instructions and adapting autonomously. Humans are directors, not laborers. You imagine the economics as you watch. Launching tons of material from Earth into orbit is costly, millions of dollars per kilogram. But here, materials arrive where they already exist in space. Metals extracted from asteroids, water converted to fuel, components printed in orbit, the need to fight gravity diminishes. Costs drop not by magic, but by rethinking the flow of resources. Production becomes more sustainable, more efficient, more attuned to the environment of space itself. The factory begins with small projects. A structural truss. A solar panel frame. A storage tank. But each small success builds confidence. Designs evolve. Systems improve. Knowledge accumulates. The factory is both a workshop and a laboratory, a place where techniques are refined and scaled. Lessons learned in microgravity feed back into software, robotics, and engineering design. You notice the quiet transformation of purpose. Asteroids, once distant rocks, become suppliers. Metal-rich cores are melted and reshaped. Water becomes propellant and life support. Microgravity enables designs impossible on Earth. The architecture of space expands not with haste, but with deliberation. Collaboration emerges subtly. Robotic units communicate. Data flows between modules. One printer completes a beam, and another aligns it with a structure assembled hours ago. Every part contributes to the whole. The factory is not a chaotic tangle, but an orchestrated ecosystem. You feel the rhythm of time stretching. Without the urgency imposed by Earth's gravity, processes can unfold gradually. Metals cool naturally, vapor condensation happens slowly, sensors calibrate themselves carefully. Patience, rather than speed, becomes the guiding principle. Machines learn from errors. Algorithms adjust. Sensors recalibrate. Redundant units stand by. Every improvement feeds the next iteration. The factory evolves organically, like a living organism in metal and circuitry. You drift through a conceptual corridor of modules. One handles solar concentrators. Another prints pressurized habitat walls. A third manages propellant storage. A network of sensors ties everything together, offering feedback loops. Even in the vastness of space, efficiency emerges through careful design and observation. The factory is not solitary. It relies on upstream mining operations on asteroids and possibly lunar depots. Materials flow along orbits, arriving predictably, ready to be transformed. Downstream, spacecraft are built, serviced, and fueled. The factory is a node in a network, an anchor for activities spreading across the inner solar system. You sense the quiet implications. Once established, such factories could enable sustainable exploration. Mars missions, lunar bases, asteroid operations all benefit from locally produced materials. The limits imposed by launching from Earth diminish. Infrastructure grows, first slowly, then with accelerating confidence. You notice how the perception of labor changes. Humans need not endure the vacuum. Humans need not mine the asteroids directly. Instead, intellect, planning, and ingenuity extend themselves through robotic agents. The factory represents a synthesis of thought and machine, where intention manifests without immediate physical presence. And in this quiet vision, you sense the beginning of something larger. Beyond this factory, networks of similar facilities may arise. One orbiting near the moon, another near an asteroid, a third in deep solar orbit. Each linked by logistics and communication. Each capable of producing components that allow expansion without overburdening Earth. Civilization begins to stretch subtly outward, layer by layer, piece by piece. You feel the elegance of microgravity engineering. Structures impossible under Earth's gravity are feasible here. Rotating habitats, massive solar mirrors, long connectors between modules all emerge from patient accumulation of parts. Even mistakes can be corrected gradually, without catastrophic pressure, because space imposes silence and distance. And still, you ask the question softly. Who will lead this first effort? Which engineers, which agencies, which companies will take the first steps? Will the venture be private, public, or a hybrid? Will collaboration across nations accelerate progress, or will competition define the pace? These questions hover like stars beyond the factory walls. The metal, the water, the robotics, they are tools. The human mind shapes them. Decisions made on Earth, careful and deliberate, become the protocols guiding assembly millions of kilometers away. Each beam printed, each module joined, is a whisper of intent stretching across space. And finally, as you drift among these imagined arms and mirrors, you sense the subtle wonder of the moment. A factory that never touches Earth, yet is inseparably linked to it. A place where starlight melts metal, where machines assemble what humans dream. A quiet revolution, unfolding not with clamor, but with precision and care. And as the factory continues its silent work in your mind, one thought lingers softly, inviting contemplation. If the first factory exists, who builds the builders and what becomes of the next generation of machines? You begin with thought. Somewhere on Earth, in offices, labs, and clean rooms, people are planning. Engineers with notebooks full of diagrams. Scientists calculating trajectories. Programmers refining code that will one day guide autonomous machines millions of kilometers away. Decisions made here echo into the void. Human intention becomes the blueprint of distant action. Not all ventures are alike. Some are private. Companies with bold visions, seeking to push technology forward, reduce costs, and stake claims in a new frontier. Their incentives are clear: profitability, market share, and prestige. They invest heavily in robotics, artificial intelligence, and orbital manufacturing. They conduct tests on Earth, in labs, in vacuum chambers, in parabolic flights that simulate microgravity. Every experiment brings them closer to sending machines into real space. Some are national. Space agencies approach with caution, their goals encompassing research, exploration, and long-term planning. Their missions balance science, safety, and diplomacy. They may deploy prototypes, collaborate with private firms, or invest in foundational technologies. Their perspective is broad. Space is not merely a resource, but a domain where humanity must learn responsibility. You sense the convergence. Private ambition meets public oversight. Risk tolerance varies, but the shared goal remains: the first space factory must work. It must operate reliably, efficiently, and autonomously. Success or failure will define the future trajectory of extraterrestrial industry. And the machines themselves? They are both instruments and apprentices. The robots built for asteroid mining and orbital assembly are not static. Each iteration learns from experience. Sensors capture minute details, torque applied to a drill, heat generated during sintering, momentum imparted when manipulating a beam. Algorithms adjust. If one machine discovers a better way to align a panel, that knowledge is uploaded to others. Machines teach machines, silently, persistently, with no fatigue or hesitation. You begin to see the hierarchy: humans design and oversee. Machines execute. Machines refine. Machines multiply knowledge. Each generation improves the next, until human hands intervene only for guidance or correction. Autonomy deepens. On Earth, humans can monitor every motion. In orbit, delays in communication become significant. Even near-Earth asteroids may be minutes away in light-speed delay. For more distant operations, hours pass between command and response. Machines cannot wait passively. They must analyze, decide, and act with intelligence that is practical, focused, and constrained to objectives set by their designers. You feel the quiet tension. Trust must be placed in systems you cannot physically touch. Every component, every software routine, every sensor must be robust, redundant, and resilient. Failure is costly, both in time and resources. But within those constraints, creativity emerges: adaptive algorithms, self-repair routines, error correction, even learning from unanticipated situations. Consider the logistics. Asteroids differ. Composition, size, spin, orbit, each variable demands customization. Robots must adjust their approach. Anchoring mechanisms, drilling patterns, energy management, and movement trajectories adapt dynamically. Software must be flexible, yet precise. Machines are tailored to environments they will only ever experience remotely. And humans, watching from millions of kilometers away, become participants in a delicate dance. Observation, analysis, and intervention are guided by data. They are mentors in a quiet apprenticeship of automation. Yet the question of authorship remains. Who truly builds the factories? The humans who design, the companies who fund, or the robots who execute? In truth, it is all of them, intertwined in a continuum of intention, action, and adaptation. Responsibility is distributed. Achievement is collective. You notice another layer. Competition drives innovation. Rival firms race to design better robotic systems, more efficient additive manufacturing processes, smarter algorithms. Speed and novelty matter. Failures teach lessons, often as much as successes. But cooperation can also flourish. Agencies share orbital positions, standards, and data. Partnerships form across borders. Intellectual exchange accelerates progress. In some cases, collaboration becomes the pathway to safety and efficiency. The frontier is both competitive and cooperative. You imagine engineers at work across the globe, one team refining AI to detect mineral veins on a rotating asteroid, another calibrating robotic arms for assembly in microgravity, yet another designing life support systems that integrate harvested water and oxygen. Each effort feeds the larger vision, a network of knowledge extending from Earth into orbit. The robots, in this vision, gain increasing independence. They may build scaffolds to support other machines. They may assemble units designed to explore or mine. The act of building becomes recursive. One generation produces the next, each layer of capability expanding the possibilities of what can be constructed. Human hands intervene less often, but oversight remains a heartbeat in the system, faint, steady, persistent. You feel the philosophical weight of it. Machines creating machines evokes a reflection on purpose. Humanity is extending itself, its ideas, its capabilities into a domain where presence is limited. Autonomy is not merely functional, it is a form of trust, a test of design, and a manifestation of intention in the absence of immediate control. Ethics enters softly. Who sets the rules? Who determines limits? If robots are assembling factories, altering asteroids, and creating infrastructure that persists for decades, human decisions carry amplified consequences. Policies, regulations, and international agreements become not just paperwork, but the invisible architecture of responsibility. You sense the subtle interconnection. Technical mastery and ethical consideration are intertwined. Companies and agencies must navigate not only engineering constraints but legal frameworks. Ownership of extraterrestrial resources is debated internationally. Collaboration may prevent conflict. Transparency becomes as important as capability. Humans must consider not just what can be done, but what should be done. And yet, the focus remains practical. The immediate task is to produce functional factories. That requires incremental progress, mining trials, robotic calibration, additive manufacturing experiments, power management, and system redundancy. Small victories accumulate. Knowledge grows. Mistakes are learning experiences, absorbed into algorithms, designs, and operational protocols. You notice how patience weaves through all layers. Space operations cannot be rushed. Even small interventions take days or weeks to plan, prepare, and execute. Microgravity, vacuum, radiation, and distance impose natural pacing. The tempo is deliberate. Humans must learn to act with the rhythm of space, not against it. And the robots reflect that rhythm. They work continuously, efficiently, without fatigue, without distraction. Their cycles are long but precise, responding to tasks as needed, adapting to microgravity, and learning from each operation. There is beauty in their steady persistence, a silent harmony with the environment. You sense anticipation. The first factories will not be monumental at first. They may produce small structural elements, test additive manufacturing techniques, and refine resource processing. But each success sets the stage for larger operations. A gradual expansion, like rings spreading on water, extends outward into the solar system. And with that expansion comes reflection. Every beam laid, every robot calibrated, every module assembled represents the convergence of human intention and mechanical execution. Machines build what humans imagine. Humans guide what machines can do. The frontier is simultaneously technological and philosophical. As you drift in thought, you feel a question rising softly. Will the first factory be born of rivalry, with companies racing to dominate? Or will it emerge from collaboration, nations and firms aligning to ensure safety, efficiency, and sustainability? Perhaps both. Perhaps the answer lies in the balance between competition's drive and cooperation's restraint. The robots continue their quiet work in orbit. Their actions are precise, deliberate, and autonomous. Humans watch, guide, and intervene only when necessary. Decisions, ethics, and design coexist in a delicate lattice of cause and effect. And as you imagine these first builders and their creations, a new thought stirs gently in your mind. The machines that construct factories may themselves require construction. Who will build the builders? And in that question lies the quiet anticipation of the next chapter, where the frontier of laws, rules, and responsibilities stretches across the borderless vastness of space. You begin with a question that feels larger than any rock or factory. In the silence of space, laws feel almost abstract. The stars do not recognize borders. Asteroids drift, orbiting the sun with indifferent patience. Yet human ambition reaches outward, and with it comes responsibility. Someone, somewhere, must decide who owns the drifting stones and who may shape them. Long before machines hummed among the stars, nations gathered on Earth to ponder such questions. The Outer Space Treaty of 1967 set a foundation. It declared space, including the moon and other celestial bodies, as the province of all humankind. No nation may claim sovereignty. No country may station weapons of mass destruction beyond Earth. The stars, the moon, and the wandering rocks belong to no one and to everyone. Yet treaties are gentle fences, guiding intentions rather than enforcing possession. They leave questions unanswered. Can you mine an asteroid if it is not owned? Can you transform it without violating the principle of shared heritage? Here, law, ethics, and practicality intersect, creating a vast, quiet expanse of deliberation. You imagine a mining robot approaching a metallic asteroid. It drills, extracts, and stores resources. To it, there is only rock and vacuum. Yet in human terms, every operation carries legal implications. International law may define limits on resource exploitation, environmental stewardship, and responsibilities toward other operators. In orbit, or even on distant asteroids, humans must cooperate to avoid conflict. Beyond treaties, policies begin to emerge. Some nations claim the right to grant permits for private ventures to extract space resources. Private companies develop internal codes of conduct. Multinational discussions explore safety, liability, and equitable access. These frameworks are not yet rigid, but they are necessary, like invisible scaffolding for an unfolding structure. Ethics enters softly. Mining an asteroid is not merely a technical or legal challenge, it is a moral one. Every operation leaves a mark. Removing metals, extracting ice, changing trajectories, these acts have consequences that ripple across space and time. Human history reminds us that resource exploitation often carries cost to the environment, to communities, and to future generations. How do we avoid repeating those mistakes beyond Earth? You consider the idea of stewardship. In the boundless vacuum, stewardship is quiet. It is not about enforcement or policing, but about foresight and care. Machines may operate autonomously, but humans design their limits, calibrate their rules, and decide what constitutes responsible action. Each decision becomes a quiet meditation on ethics, technology, and the unknown. The practicalities of space law are subtle. Liability is one. If a robotic mining mission accidentally collides with another spacecraft, or fragments of an asteroid drift into orbit and threaten satellites, who is responsible? If resources are extracted, who benefits and who ensures fair access? Questions of property, liability, and equitable use intertwine like the orbits of asteroids themselves, slow, predictable, yet endlessly interacting. You float in thought, imagining an international monitoring system. Satellites track asteroid operations. Data streams provide transparency. Missions are coordinated. Conflicts, like small gravitational tugs, are anticipated and mitigated before they escalate. Space becomes a governed frontier, not through force, but through shared intention and communication. And yet, there is room for uncertainty. Laws evolve slowly, often lagging behind technology. Private ventures may push boundaries, testing the limits of treaties and regulations. The potential for disputes remains. But even in uncertainty, the dialogue itself is part of the frontier, a negotiation between ambition and responsibility, exploration and stewardship. You reflect on environmental considerations. On Earth, mining leaves scars, mountains reshaped, rivers diverted, ecosystems disrupted. In space, the scale differs, but the principle remains. Even in microgravity, debris must be managed. Dust clouds can interfere with operations, collisions can create hazards, and altering the trajectory of an asteroid could, in theory, create risks to Earth. Precaution, foresight, and careful planning become ethical imperatives. Your mind drifts to the notion of shared benefit. Resources extracted from space are vast compared to what any one nation or company could use. How can humanity ensure that these resources contribute not only to profit, but to collective progress? Could water mined from an asteroid support international space stations? Could metals form components for cooperative scientific missions? These possibilities emerge gently, suggesting that law and ethics are as essential as technology itself. Even the idea of ownership is subtle. Treaties prevent sovereignty, but not use. Private companies may claim extracted resources without claiming the body itself. The principle is delicate. The asteroid remains unowned, yet its contents may be utilized. This distinction may guide how operations proceed, allowing exploration while preserving the essence of a shared cosmos. You sense the role of transparency. Public reporting, international oversight, and open collaboration create trust. Without it, even the most peaceful missions could lead to misunderstanding or conflict. A quiet system of accountability spreads across millions of kilometers, as if humanity's attention must extend alongside the machines. And technology reinforces law. Autonomous mining requires coding ethical and legal limits directly into machines. A drill must stop when it reaches a boundary. Propellant use must adhere to agreements. Orbital maneuvers must avoid prohibited zones. Software becomes a subtle mediator between ambition and responsibility. In this reflective moment, you feel the weight of history. Earth's resources were once thought limitless. Societies built entire economies on extraction, often with short-term gain in mind. Space offers a chance to do differently. Perhaps humanity can combine curiosity, ingenuity, and foresight to build a framework where resource use, exploration, and preservation coexist. You imagine committees and councils discussing policy not with urgency, but with meditation, considering not just today's gains, but decades, centuries, or longer. Space is patient. You recognize that this framework, legal, ethical, and practical, is as essential as the machines themselves. Without it, factories, mining missions, and infrastructure risk unintended consequences. With it, the frontier becomes a place of responsible expansion, where curiosity is guided by conscience. And as you drift alongside imagined asteroids and orbiting factories, your thoughts settle on a quiet reflection. Humanity can explore, harvest, and build, but only if wisdom travels with ambition, and if law and ethics accompany every robotic hand in the vast, borderless dark. And in that quiet understanding, you sense the next tension softly emerging, the fragility of the machines, the dangers that await, and the risks inherent in this silent, unyielding environment. You begin with silence. Not the comforting silence of a quiet room or a calm night, but the absolute silence of space, a vast, unbroken expanse where sound does not travel, and where danger moves unseen. In this emptiness, even the smallest miscalculation can ripple outward with consequences that are invisible and profound. Space is indifferent. Radiation streams relentlessly from the sun and beyond. High-energy particles pass through metal and flesh alike, damaging electronics, altering circuitry, and slowly wearing down materials. Cosmic rays, solar flares, and charged particles bombard everything that ventures beyond the protective bubble of Earth's magnetosphere. Even a tiny, unshielded sensor can degrade, and yet, these sensors guide entire factories, ensuring precision in assembly and mining. Micrometeorites drift silently, tiny fragments traveling at incredible speeds. They can pierce metal panels, disrupt machinery, or scatter debris that threatens other modules. In orbit, collisions are unforgiving. There is no atmosphere to slow down a projectile. Even a grain of dust becomes a bullet, moving with kinetic energy that dwarfs its size. Robots must endure extremes humans cannot. Temperature swings between sunlight and shadow can span hundreds of degrees. Materials expand and contract. Lubricants behave differently. Electronics must tolerate both blistering heat and freezing cold. Every joint, every actuator, every circuit is tested against forces it was never designed to feel on Earth. Yet these machines are expected to perform continuously, sometimes for years, without repair. You imagine a robotic arm extending toward a metallic asteroid. It grips, drills, and maneuvers with careful precision. A tiny misalignment could damage the arm, halt production, or trigger a cascade of errors. Contingency plans exist, of course. Redundancy is built into every system. Duplicate units, backup power supplies, and multiple communication channels allow operations to continue even if one component fails. But redundancy cannot prevent every problem. Fragility is a constant companion. Software bugs, sensor drift, or unexpected material behavior can propagate. A printer may deposit molten metal incorrectly. A robotic gripper may misalign a truss. Even with autonomous correction, small errors can accumulate, turning minor setbacks into mission-critical failures. The farther from Earth, the slower the feedback loop. Humans cannot intervene instantly. Decisions must be made ahead of time, anticipating failure and embedding resilience into both machines and protocols. Space is beautiful but unforgiving. You float alongside a metallic asteroid, watching sunlight reflect across its irregular surface. The rocks are mesmerizing, ancient, silent. And yet, just beyond the glow, danger is constant. A fragment of debris may drift unnoticed. Solar storms may surge unexpectedly. Electronics may falter. The beauty of the cosmos is inseparable from its perils. Appreciation and caution are inseparable companions in this realm. You consider the role of shielding. Water tanks, metal plating, and specialized materials absorb radiation and buffer impacts. Orientation can minimize exposure. Redundancy in power systems and communication links ensures continuity. Even in microgravity, protective design is an art of balance. Too much shielding adds mass, too little invites risk. Every choice is a trade-off between performance, efficiency, and survival. Yet, despite all preparation, uncertainty lingers. You imagine a robotic factory assembling trusses for a distant habitat. Suddenly, a micrometeorite pierces a storage tank. Electronics falter. One system shuts down, and the entire workflow pauses. Autonomous protocols attempt recovery. Sensors recalibrate. Algorithms adjust. Still, human engineers must respond, remotely diagnosing problems with data that has traveled millions of kilometers. Every second matters. Every decision must balance caution with necessity. Fragility also extends to logistics. Supply lines from Earth are expensive and infrequent. Propellant, spare parts, and technical expertise cannot arrive instantly. A failure of a critical module could halt operations for weeks or months. Contingency planning requires imagination, foresight, and precision. Every system is designed not only to work but to fail gracefully, recovering from the unexpected without catastrophic consequences. You notice the paradox: the very scale that makes space factories transformative also magnifies vulnerability. A small error in microgravity can ripple across kilometers of structure. A misalignment in one robotic arm can delay entire assembly sequences. A minor design flaw in an additive manufacturing unit can compromise a habitat wall. The machines are strong, yet they are also delicate, operating in a medium that rewards precision and punishes mistakes. And humans, though distant, are never absent. They monitor, analyze, and intervene. Algorithms flag anomalies. Engineers review telemetry. Decisions are made with calm deliberation, guided by experience, intuition, and an awareness of the profound consequences. The human heartbeat, measured in patience, not speed, remains present even across millions of kilometers. You think of examples on Earth. Industrial failures are instructive, but forgiving. A factory can be evacuated. Machinery can be replaced. In space, these luxuries do not exist. Every component must function. Every system must anticipate hazards that are invisible and relentless. Risk is embedded into the very fabric of the endeavor. Yet, risk is not merely technical. Economic pressures, competition, and deadlines may encourage bolder choices. Even with the best planning, humans and machines alike must navigate uncertainty. Decisions to proceed with operations are weighed against potential consequences, balancing ambition with prudence. Space rewards those who respect its laws, and punishes those who disregard them. And still, progress continues. Engineers design for redundancy, reliability, and resilience. Robots evolve to detect and respond to anomalies. Learning algorithms allow machines to adjust to unexpected conditions. Each successful operation increases confidence, expands knowledge, and reduces the probability of failure in future missions. You drift among imagined factories and depots. They hum quietly, machines working tirelessly, aware only of tasks, physics, and protocols. Every arm, every printer, every sensor is an exercise in trust, in design, in planning, in foresight. And in this quiet meditation, you sense the fragility alongside the ambition. Space is patient, yet unforgiving. Factories float like delicate blossoms against an infinite dark. Radiation, debris, technical failure all remind you that even the most sophisticated systems are subject to the rules of the cosmos. Each mission succeeds not only because of intelligence and skill but because of humility and preparation. And as you drift, contemplating these silent, distant dangers, one thought lingers softly: what happens when a factory fails millions of kilometers from home? And who will pick up the pieces of a dream suspended in the void? You begin with the sweep of perspective. From Earth, the night sky appears vast and still, dotted with faint pinpricks of light. But imagine drifting beyond, high above the clouds, watching the solar system slowly stir. The moon glimmers, Mars casts a red shadow, and asteroids glide silently along their ancient paths. Here, beyond your immediate reach, quiet change is underway. Infrastructure grows not as monuments, but as persistent effort. Lunar bases extend carefully along regolith plains. Solar panels shimmer in the low gravity, reflecting sunlight to supply energy. Habitats rise, partially buried to buffer radiation, modular in design, connected by corridors and robotic service systems. Each structure is small alone, but collectively they form a network, a slowly maturing web of human presence. Mars too awakens, subtly at first. Robotic explorers, once alone, begin constructing landing pads, greenhouses, and storage depots. Water is extracted from ice beneath the surface. Solar arrays track the sun with quiet precision, powering drills, printers, and environmental controls. The planet's rust-colored plains host small, deliberate activity, soft expansion rather than explosive growth. Asteroid depots punctuate the space between worlds. Metal-rich and water-bearing rocks, once distant and untouched, become nodes in a logistical web. They are mining stations, refueling points, raw material caches. Robots work tirelessly, processing metals and water, assembling components, testing structures. These depots are functional, austere, yet profoundly transformative, the hidden scaffolding of a solar system awakening. You notice the rhythm of progress. Activities are persistent, almost meditative. Operations unfold day by day, orbit by orbit, with no urgency beyond the cadence of the tasks themselves. Resources are harvested, processed, and transported with careful precision. Systems are monitored, updated, and maintained continuously. The pace is deliberate, and in this deliberation, you sense elegance. Civilization spreads without fanfare, moving through patience, intelligence, and adaptation. Machines extend human presence. Robotic miners, printers, and assemblers operate where humans cannot yet dwell. They prepare landing sites, assemble habitats, maintain depots, and transfer resources. Autonomy is essential. Light-minute delays prevent direct control. Algorithms learn from mistakes, refine motion, and optimize efficiency. Humans watch, guide, and plan, but machines do the daily work, gently bridging the distance between thought and action. You imagine coordination across vast distances. Each lunar module, Martian greenhouse, and asteroid depot is a node in a web. Communication links transmit telemetry, operational status, and environmental data. Data centers on Earth process information, refine algorithms, and upload updates. Decisions are made considering thousands of variables: orbital mechanics, resource availability, power constraints, and weather patterns on Mars or the Moon. Yet despite complexity, the system hums quietly, like a living organism adapted to space. Infrastructure reshapes perception. The solar system no longer seems an empty wilderness. Even small robotic factories, landing pads, and depots suggest permanence. Human ingenuity extends subtly, layer by layer. Networks of equipment, energy, and information create a sense of place, a feeling that these distant worlds are becoming home, not with the noise of conquest, but with the soft rhythm of methodical expansion. Resource distribution becomes part of the system. Water from asteroids supports lunar greenhouses. Metals harvested in orbit feed construction robots. Propellant produced at depots refuels spacecraft traveling between nodes. Infrastructure grows outward, linking planets, moons, and asteroids in a functional web. Expansion is not chaotic, it is planned, cumulative, and adaptive. The solar system becomes more navigable, more interconnected, and more supportive of life step by step, quietly, persistently. You notice the cumulative effect on humanity. Knowledge gained on Mars informs lunar operations. Lessons learned from asteroid mining improve orbital factories. Habitats evolve with each iteration. Designs become modular, resilient, and efficient. Every success, no matter how small, accelerates the next achievement. The solar system is waking, not through sudden leaps, but through careful, steady effort, each operation building upon the last. You reflect on civilization's character in this context. Expansion does not need to be loud. It does not require fanfare or spectacle. Steady, persistent growth, guided by observation, planning, and adaptation, shapes a resilient, flexible civilization. Machines perform daily labor. Even the challenges are absorbed gracefully. Radiation, dust, orbital debris, and mechanical failure continue to test systems. Yet the network is designed with redundancy, repair routines, and adaptive planning. Machines learn. Humans anticipate. Contingency is embedded. Fragility is addressed not with fear, but with preparation. Risk is understood, managed, and incorporated into the fabric of expansion. You sense the continuity across scales. From a single lunar habitat to an asteroid depot, to a Martian greenhouse, each element is part of a connected system. The solar system's awakening is not fragmented, it is coherent. Operations are interdependent. Water supports life support systems. Metals support construction. Energy networks power exploration. Knowledge flows across space, feeding both machines and humans. And in this web of activity, you see potential. Once infrastructure is established, opportunities multiply. Scientific missions reach further. Habitats expand. Transportation networks evolve. Trade, supply, and communication systems form. Civilization grows organically, leveraging local resources, guided by intelligence and foresight, amplified by machines that extend human will. You feel the wonder of scale. The solar system, once perceived as distant and isolated, becomes an interconnected stage for exploration and industry. Each asteroid, moon, and planet is a node in a living network of activity. Machines hum, habitats breathe, and the rhythm of expansion is gentle, persistent, and deliberate. Human presence is felt not as overwhelming noise, but as careful, steady cultivation. You notice the philosophical dimension. This growth is not conquest. It is stewardship. Expansion respects the environment, leverages autonomy, and prioritizes sustainability. Machines, resources, and humans are integrated in a system designed for longevity, adaptability, and resilience. Civilization spreads softly, thoughtfully, and deliberately, an echo of earthly wisdom carried into space. And as you drift among these imagined nodes, a question arises softly in your mind. If expansion is measured not in leaps, but in persistent effort, how far can civilization reach before ambition outpaces patience, and how will the solar system look when every node hums with life, work, and quiet presence? And in that lingering curiosity, you sense the gentle transition to your next thought, returning to Earth, where observation, reflection, and imagination bring the vastness of space back to the stillness of your own breath. You begin with your own breathing. The air moves softly in your lungs. Each inhalation and exhalation is steady, rhythmic, grounding. The earth beneath you feels solid, familiar, yet your mind drifts outward, beyond the atmosphere, beyond the blue glow of clouds, past the moon, past Mars, and into the quiet paths of asteroids circling the sun. You are both here and there, tethered by thought. Look up. The night sky stretches above like an infinite canvas. Stars shimmer faintly, but the pinpricks of light are not the only motion. Between the dots, rocks, asteroids, wandering silently, drift through their ancient orbits. They carry metals, water, and ice. They are the raw materials of the future. Some may one day be transformed into habitats, factories, or fuel stations. They orbit in silence, waiting for human curiosity and ingenuity to reach them. You feel the quiet connection between imagination and action. What begins as a thought on Earth, a diagram on a whiteboard, a line of code, a plan in a laboratory, can manifest millions of kilometers away. Machines will carry intention into the void. Robots will drill, refine, and assemble. Factories will float in orbit. Resources from asteroids will become tools, components, and fuel. The dream of space infrastructure is already in motion, even before the first orbiting beams are joined. Reflection settles softly. Every human endeavor starts with curiosity. Early astronomers charted the heavens with careful eyes, noting the wanderers among stars. Miners extracted metals from Earth's crust, learning patience and precision. Engineers built machines that could operate beyond the reach of human hands. And now, that lineage extends beyond Earth itself. Each step is deliberate, informed by the successes and failures of the past. You sense the intertwining of human and machine. Machines will build structures, extract resources, and support habitats. But humans remain essential. You design, you plan, you calculate, and you imagine. Machines execute. Machines learn. Machines adapt. And in this partnership, the solar system slowly becomes a place where human intention and robotic action coexist, quiet, persistent, and careful. Think of the first factories, orbiting patiently. Metal is melted and shaped in microgravity. Robotic arms assemble trusses, mirrors, and walls. Water is separated into hydrogen and oxygen. Fuel is stored for journeys to the Moon, Mars, or deeper into the solar system. Each action is methodical. Each success, no matter how small, is a testament to preparation, ingenuity, and trust in design. Even the risks are part of the story. Radiation, micrometeorites, mechanical failure, software errors, all are challenges to be acknowledged, planned for, and mitigated. Fragility coexists with resilience. Redundancy, careful monitoring, and autonomous correction form a safety net. Each obstacle teaches lessons, embedding knowledge into both human and machine. The vacuum is indifferent, yet preparation transforms peril into possibility. You contemplate the slow expansion of civilization. Lunar bases, Martian outposts, asteroid depots, all interlinked by logistics, energy, and information. Machines hum, habitats breathe, and the solar system becomes a network, quietly supporting exploration and industry. Civilization grows softly, deliberately, and sustainably, layer by layer. The expansion is measured not by spectacle, but by persistence and coherence. And yet, everything begins here, in your reflection. You breathe. You observe. You imagine. Every thought of mining asteroids, building orbiting factories, and constructing a network of habitats is seated in your mind, nurtured by curiosity. The desire to explore, to understand, and to create is the spark that ignites distant action. Every innovation on Earth reaches outward, carried by intellect and intention. You feel the subtle rhythm of responsibility. To reach beyond safely requires foresight. Legal frameworks guide action. Ethical principles shape decisions. Resources are extracted thoughtfully. Machines operate within constraints designed to protect, to sustain, and to optimize. Expansion is not only possible, but also intentional, careful, and guided by principles that honor both the cosmos and human values. The horizon of possibilities stretches infinitely. Who will construct the first orbital factory? Who will master asteroid mining? Which robots will be entrusted to build the next generation of machines? Which humans will design, calculate, and oversee? Every future endeavor begins in the quiet imagination of today. The intentions you set, the questions you ask, and the curiosity you nurture ripple outward into reality. You sense a connection to every human who has ever looked upward. The astronomer charting planetary paths. The engineer designing a machine that can operate in vacuum. The miner extracting rare metals. The scientist calculating trajectories. Each contributed to the quiet knowledge and persistent effort that now allow you to imagine a solar system slowly filling with activity, life, and purpose. And in that imagining, the factory exists already, if only in thought. Metal floats, robotic arms extend, water is transformed into fuel. Machines hum with invisible rhythm. Solar arrays glimmer, trusses stretch, and habitats form layer by layer. The first factories, the first depots, the first infrastructure, they exist in the potential of human intention, ready to emerge when curiosity meets capability. You feel the gentle optimism of possibility. Even as Earth remains your grounding point, your imagination allows you to traverse the solar system. You see infrastructure taking shape. You see machines working tirelessly, guided by human foresight. You see risks mitigated and challenges overcome. The universe, vast and silent, becomes a canvas for deliberate, thoughtful expansion. And now, in the calm of your own breathing, you ask quietly, who will build them? Which humans will guide the first factories? Which robots will extend the reach of imagination? And, in the quietest part of your mind, do you sense that, in some small way, it could be you? You close your eyes, letting the thought linger. The stars drift silently above. The solar system hums with potential. Machines, humans, and intention intertwine. And as sleep approaches, you allow yourself to drift into that gentle unknown, carrying the quiet wonder of what might be a civilization softly awakening, one carefully placed piece at a time. The night is vast. The cosmos waits. And somewhere in that expanse, the first factory is waiting for its builders.